So welcome back, everybody. And I wanted to give a quick reminder of what we did last week and put that in connection with both the project and the things we need to code. And as you see, there's also a suggestion for paths for the next project. And this depends very much on your interests. But what I wanted to do now is actually to say a little bit more about the gates, which we're going to look at. And for some of you, this may be well known, but we need that in order to link specific operations like rotations to the variational quantum eigensolver. So one of the reasons why we use this variational quantum eigensolver instead of the original algorithm, which was introduced in the very beginning, which is called a quantum phase estimation algorithm, and that's based on quantum Fourier transforms. That's because this algorithm gives very long circuits, which means that in today's quantum computers, we would have to have states which have a long lifetime to be able to operate on them. And when the circuits get very long, what happens then is that the practical implementation of a quantum mechanical algorithm to find the eigenvalues becomes simply unfeasible. So this quantum eigensolver or variational quantum eigensolver is based on the variational principle, which many of you may have heard of. I will remind you of that. So it's the variational principle, which is not the one you may be familiar with, which is called Schrödinger's variational principle, where you can actually derive the Schrödinger equation from the expectation value of the energy. And that's based on variational calculus. But this is a slightly different variant of the same principle. And when we have that, we are going to use the variational principle and set up an ansatz for the wave function. This ansatz is highly related with the different items we have to program in the project. So we are going to start with a 2x2 matrix, which you have seen ad nauseam now many times. And we are going to rephrase that in terms of a 1-qubit case. And we're going to look at how we can actually perform the simulation with an ansatz for the lowest lying state. So this variational quantum eigensolver, the way we are going to describe it and implement it, is a mix of a classical solver and a quantum mechanical solver. The classical part is where you're going to optimize in order to find the best optimal parameters. So in the variational quantum eigensolver, there is an optimization part. So these are the kind of back and forths which we are going to discuss. And the reason why I wanted to bring up a little bit about this kind of perhaps not too exciting topic about gates, different types, is simply because that's going to motivate the type of operations which we will do in order to set up a ansatz for the trial wave function. And when I'm saying this, the ansatz is going to be based on a 1-qubit transformation on the so-called Bloch sphere, which we will remind you about, in terms of rotation matrices. So the angles of a rotation matrix, they become parameters which we want to optimize to find the best possible representation of the energy. So this is a kind of, how to say, more overarching view on what we will be doing today and also in the next weeks. Now, there's another thing which Karen and Ruben told me from last week, is that some of you wonder whether we could collaborate. So of course you can collaborate on the projects. And this is often very helpful because then, as I mentioned, I think I mentioned in the beginning, if you collaborate 2 or 3 together, somebody may be a wizard on computing, somebody may be very knowledgeable in mathematics, and then somebody like me, and I think somebody has heard it already, is good at making coffee and cracking bad jokes. Yeah. So this is something you can decide. So there are 2 typical possibilities. So you can hand in a common report, and then you obviously get all the same grade. obviously, or you can collaborate, and then you write your individual reports. So we've had groups who've been acting like that. And then you will simply state that we've been collaborating on the code development and so on, but we wanted to write our own individual reports. So this is up to you. And there's obviously nothing which hinders you from just working by yourself. But collaborating is always very useful because you gain a lot by talking to other people. So feel free to find your optimal format. Now, the other thing I wanted to say something about is obviously also the project number 2 here. And there are at least 2 options, which I came up with. So I know that somebody is much interested in quantum machine learning as well. So the first project is more to get everybody up to the same speed, even if there may be elements of repetition for some of you. And then the second project, we have the possibility to both look at quantum machine learning. I know that some of you would like to explore other algorithms. So in the first project, we are forcing you into this quantum mechanical applications of quantum computing. And that's essentially because that's my line of research and my main interest. But there is nothing which hinders us to look at other algorithms. And after the Easter break, we will also go more in details into, let's say, quantum Fourier transforms and other algorithms like Grover, Shor, and so on. And this depends a little bit on what you guys are most interested in. So we can always split a little bit, but during the lectures, we will have to focus on one selected topic. But we can make a project on quantum machine learning, which could also, for those of you taking the course on machine learning, one could perhaps combine the two. Then there are obviously other possibilities, and this depends very much upon you. So remember again that in principle, this is a kind of self-study course. So if you have other ideas, I know that some of you are dealing with educational research in quantum mechanics. So if you would like to develop, let's say, exercises or projects or demonstrations of quantum computing for, let's say, people who have not studied quantum computing or quantum mechanics, this is another possibility. Okay, so I want this second one to be much more open and something which you can define, which aligns more with your research. I know that some of you are more interested in actually making quantum gates and to simulate systems with specific gates. That's another possibility. So just keep it in mind when you work on project number 1 and see if there are specific things you would like to do. I'm a strong believer of individually tailoring courses. I've always been. It takes more time as a teacher because then you have to make something which is special for everybody, but it's much more fun. For me, it's much more fun to teach because I learn much more. Okay, so there are some readings and I put in this paper by Tilly et al., which is a long review on the VQE. But we are going to step you through the basic elements so that at the end, you have all the ingredients which are needed for project number 1. Now, I just wanted to quickly go a little bit back to what we discussed last week. And some of you had problems with some of the Qiskit packages, which I provided. So Ruben and Karen, they actually, for those of you at the lab, they had an alternative to the one which I had put up in the original Jupyter notebook. So you would install this Qiskit IBM provider, and that would be the only thing which, in case you were not able to install that package which I have been using. So this depends a little bit on Unix and Linux distributions or distributions you have and how everything is set up, which Python version you have, etc., etc. So the setup is the same. If you want to use these IBM machines, you need to set up an account. And the thing which is now possible, as we discussed last time, is that you do actually have access to the 127 qubit machine. and you can make runs. You will probably see that it will take you will have to spend a long time in the queue. And that's simply because there are many people using them. And if you have not paid, I mean, your priority is pretty low in how you advance in the queue. But you can still run it on a real quantum computer. Now, the thing which we did last week was to look at the Bell states, which is something you have to start with in a project. This is more meant as a kind of pedagogical introduction to writing a code or setting up states, acting on these with a specific matrix, like this Hadamard matrices, which is something we also call for a gate. And then when you've done that, we have to make a measurement. So all these elements are elements which we discussed last week, but using Qiskit. But then for those of you who had the possibility of staying here, both Karen and Ruben discussed also how to actually start writing your own code. So you can use Qiskit to compare your code with, so just to see that things are running correctly. Qiskit is a very powerful tool. You probably saw I sent you an email earlier today with links to educational material, libraries, and so on. I hope you don't mind if I send you this kind of links and hints, because there's a lot of material out there. And many of these videos developed by IBM and many other ones, they are very pedagogical, many of them. Okay, any questions so far? So this was a quick thing about the what we did partly last week. So if you go back last week, we also looked at some of the gates, but we had a more focus on actually starting to write the code. Next week, we will also have a more hands-on session in the second lecture. But the first lecture we are going to more use as a theory lecture, where we will focus on how we actually set up a VQE code in an efficient way. So that we are going to throw in elements now and then, so that at the end, you have all the elements which are needed in order to run the calculations for a simpler quantum mechanical Hamiltonian with the variational quantum eigensolver as algorithm. Okay, any questions so far? Feel free to interrupt me. For those of you online, feel free to ask questions, because I'm going to switch over to the whiteboard, because I wanted to remind you of some of the gates and some of these technicalities, because there are some technicalities which will become very useful when we are running the simulation. So let's switch over to the Jupyter, no, to the whiteboard. So when we are setting up these operations, what has become a tradition in quantum computing, I mean, basically since the beginning, is to draw everything as circuits in terms of gates, but these are nothing but matrix vector, matrix multiplications. So that's the way we will translate these mathematical operations. So let me remind you of some of the basic gates and what they are doing. And the reason why I'm doing this is that I want to bring up the rotation matrices, because these are quantities and operations which we will use in setting up an ansatz for the trial wave function. So this is perhaps not the most exciting part, but let us just repeat some of these important gates. So we have what we called for 1 qubit gates. And the typical way you would write this, so you have some initial state, phi, and then you perform an operation. This is often depicted as a box here. There's actually a very efficient LaTeX package, if you're familiar with LaTeX as a mathematical typesetting tool, which is called TIKC. which has been extremely, yeah. Oh yeah, let me just put it down here. So I can, so let me just finish this one. So this is a G for gate, and that gives us a transform state phi prime. Now there is a software which is called with LaTeX. So you would need to have installed TIKC. So this is just a digression, which many of you are familiar with. Actually, the person who developed TIKC was a person who developed this slide package, which is called Beamer, which is extremely popular. And the one which being used is Quanti-KC. There are many packages, actually. This is not the only one. And this is extremely useful if you want to draw circles. So it uses basically the sort of table environment in LaTeX, not the table environment, something which looks like table or a matrix environment. And they have defined several of the symbols which we are going to look at. So what it means, this operation, which you see now, this is a simple circuit. We are not performing a measurement. So we are just performing an operation. That means that the new state, this phi prime, is simply given by this G multiplied with the initial state. And we have already met some of them. And we know that we have the sigma x. And I'm going to simply use from now on the notation x for that. And we know that on a 1 qubit state, it flips a qubit. So this gate here flips a qubit. And the way this acts, when it acts on qubit 0, it just gives us qubit 1. So we're saying it flips a qubit. That's what is meant with that one. Similarly, from now on, I will call the sigma y for just a y gate. And this one is a gate which flips a qubit and multiplies it with the imaginary number I. So that means that if I act with y on 0, this is the same as I times 1. So these are some basic operations, and it's pretty easy to see that if you set up the matrices and multiply them with the vectors. So when you see a circuit like the one here in its simplest form, what it means is a matrix vector multiplication or a matrix matrix. So when you're writing your code, what you need to encode are actually the states encoded as vectors, and then the different gates encoded as matrices. And then we have the sigma z, which is a fundamental one. And we know that z acting on 0 just gives back 0. And z acting on 1 gives us minus 1. So what we say then, if we have 0 and 1 as our computational basis, then we know that the z gate has these as eigen pairs. 1 with eigenvalue plus 1 for 0 and minus 1 for 1. And that's very important because we will use these two states here very often, or tens of products of these, as our computational basis. So we are going to rewrite many of the Hamiltonians in terms of C gates. And there are some operations which allow us to do that. And this is one of the reasons why I bring this up, because we will have to rewrite some of the Hamiltonians in order to perform the operations on a computational basis, because at the end, we will make a measurement. And this measurement is something which we want to give us what is a projection of one of the computational basis states. Okay? So even if there is a strong element of repetition here, I hope you can convince you that there is something useful in what we are doing now. So the S gate is another one. And this is a gate which actually rotates the states around an angle of pi half, of 90 degrees. And it's normally called a phase gate. So what it does, it actually is you will often see this called a phase gate, because you know that e to the power of I, p half, gives us I. You know that this quantity here is the same as e of pi half, okay? So this corresponds to when we now have defined this rotational matrices, you will see that this is going to correspond to a rotation around the z-axis by 90 degrees. And it's often called a phase gate, and we are coming back to that, because this factor e to the pi half is then a so-called phase. There are other famous gates. There's something which is called the t pi divided by 8 gate, or just a t gate, and that is given by a rotation around the z-axis of 45 degrees. So this is 1, 0, 0, and e to the I of pi divided by 4. Now, the matrices which we are interested in now are the rotation matrices. So we are going to have a rotation matrix, Rk, which is given in terms of 1, 0, 0, and then I have a e of 2 pi divided by 2 to the power of k. And we are going to look at a more explicit form and just link why these are called rotation matrices. Yeah. Yeah. So if you think of your computational basis, you for 1 qubit, we have chosen this as a computational basis. So in just a few moments, I'm going to draw or try to draw a sphere, which is called the Bloch sphere. And then 0 could be the North Pole on the sphere, and 1 could be the South Pole. So this would be the computational states on that sphere. Then you can rotate the states on a sphere by these rotation matrices. And we are going to use these rotation matrices to describe a 1 qubit state on the Bloch sphere, on the sphere, in an arbitrary state, given by arbitrary angles. And this is what we will use as an ansatz for the variational quantum eigensolver. I hope that will give, you will see that when I'm drawing the sphere now, that these two states here, this state and that state, are going to correspond to specific states on this sphere. Then you can make a totally general one by just rotating these states. And you will see that quickly now. And the reason why I spend some time on this now is that these serve as ansatzes for the trial wave function, which we're going to implement in a variational eigensolver. Yeah? 2k, yeah. 2 pi, I times 2 pi divided by 2 to the power of k. That's one way of defining it. I'm going to put this up in a more special way in terms of cosines and sines a little bit later. So you will see immediately why this is relevant. Then we have the other gate, which I just wanted to remind you of, which we have met many times, and that's this Hadamard gate. And this is normally always written when we have a state phi. This is the initial state. We have prepared the system in a state, and you would typically see that written in terms of a H prime, an H here. And for the two-dimensional case, which is the 2 qubit case, this H, not to be interchanged with the Hamiltonian of the system, is just 1, 1, minus 1. This gate has some interesting properties as well. This gate has the property that when I write this, so I take the transpose of it, this just gives us the identity matrix. And that's easy to see if you do the operations. So remember now that the gates we are setting up, we want them to be unitary, but not all gates represent unitary operations. So this is an important property because what comes now is something which is very useful. So if you look at this property here, so one of the things which we will use when we're going to rewrite the Hamiltonian so that we will have the Hamiltonian in terms of just the Z matrix, or the Pauli Z gate, because that's the one which projects out the states 0 and 1. We have that the Hadamard matrix multiplied with the Pauli X is actually equal to the Pauli Z matrix. So this is going to be a very useful quantity or identity which we will use. And you can see that if you just perform the operations. So this will be, and now if you look a little bit closer at the Hadamard gate, which I wrote in the previous slide, which is 1, 1, 1, minus 1, this can be written as the sum of two of these Pauli matrices. Do you see on the fly which one that could be? So let me just remind you of the Pauli matrices. So one of the Pauli matrices 0, 1, 1, 0, and then Z is 0. No, sorry, not 0, but 1, 0, 0, minus 1. Yes. So that means that what you have now is X plus Z, and this is multiplied with X, and this is multiplied with 1 over square root of 2 times X plus Z. And when we write it out, what we get then is obviously a factor of a half, and then I have X squared times X. Now X squared times X is equal to, so these matrices have an important property. Does anyone remember what that becomes? Yeah, that's the idea. Because I have X times X times X. Yeah, it's multiplied with this one. So, oh, sorry, it's not an X. Yeah, I just had to continue along the line there. Sorry. I mean, I see that. And then you get an X squared times Z. Then you get plus a C times X squared. And then you get a plus C times X times Z. Now, what you will see when you perform this multiplication, these are just matrices, not the most exciting thing we are doing. This is just a minus X. So what you have then is X squared, which is identity matrix, X minus X. And then I have X squared, which is equal to the identity matrix again. This one, which is equal to the identity matrix again. And then you have 2 times a factor 1 over half. So this is just a C matrix. Okay. This is going to be an extremely useful property. Now, you remember that HT times H is equal to the identity matrix. The inverse exists. So that means that I can actually multiply with H transposed. And you will also see that H transposed, this is a special case, is actually equal to H. You can see that immediately if you take the inverse of that matrix. I hope you don't get offended if you think it's too simple now. But you can now multiply, and you will then see that the Pauli X matrix, yeah, H transpose is equal to H. No, sorry. No, I didn't mean that. No, sorry. Yeah, I said the inverse. Yeah, sorry, actually. Yeah, thanks. So if you use that, then you can show that X is then given by H times Z times H. That's a very important property. You can repeat the same exercise with the with Y. So if I take H, Y times H, you will find that that is equal to minus Y. And you can actually rewrite. So these are similar exercises. And I leave that as a small exercise for you guys. But one of the important things is that when we have a Hamiltonian now, which contains the Pauli X matrix, we can actually rewrite it like that. So what does that mean? If you now think back to project number 1, we had now a Hamiltonian, so I'm trying to distinguish this from a Hadamard matrix, which then contained a variable C, a constant, which was multiplied with the identity matrix, plus another variable, a constant, which was multiplied with a Pauli X matrix, plus another constant, which was multiplied with a Pauli Z matrix. Now, what we are going to do now in this project, so this was a 2x2 matrix. So what we did then was actually to rewrite the Hamiltonian matrix. And this Hamiltonian matrix was now given by some matrix elements, which we put up as, so we would have 0 of H of 0. And then we had 0 of H multiplied with state 1. And then we had 1 of H of 0. And this matrix is assumed to be Hermitian. And then we had the final 1 of H of 1. Now, in general, the state which we are going to set up, the state phi, which is the ansatz now for the system, is going to be a linear combination for the 2x2 case of the computational basis state 0 plus the computational basis state 1, okay? So that means that when we are going to calculate the expectation value, so we are going to make an ansatz, and let's just mark this one. So this will be our ansatz for the trial wave function. And these alphas will depend on rotation angles. And we are going to find the optimal angles which minimize the energy, okay? So these alphas which you see and the betas which you see here will then depend on some specific operations in us preparing the initial state. So what we are going to calculate then, by running many experiments, is the expectation value in terms of the state phi. So this is a quantity which we are going to look at. So we want to calculate this one with respect to the Hamiltonian of phi here. And we are going to have some kind of linear combinations of these computational basis states, 0 and 1. We don't know which of these parameters, alpha and beta, what they should look like, but we can make some guesses. And this is the typical approach in a variational method. So this phi here, which you see, may not be the exact solution to the problem. Okay, so if you now go back to the Hamiltonian here, you see now that we are going to calculate expectation values. So we are going to have one, which is pretty trivial. So there will be one term, which is simply going to be phi multiplied with this constant. And then we have the identity matrix and phi. So this is going to be a trivial calculation, okay? And we are going to make measurements and project out specific states. And then we are going to run this many times. But let's just set up the quantities we need to evaluate. Then there is a new quantity here, which now contains the Pauli X matrix of phi. And finally, there's going to be another constant multiplied with this one, multiplied with C, multiplied with phi. So if you now look at the state which we have, this one is actually pretty trivial to calculate, because this operator here will just project out, or we know the eigenvalues, it will just act on that one and on that one. And we know what the eigenvalues are. For X, on the other hand, and now you see why we want to rewrite the Hamiltonian in terms of Pauli Z gates. Because if you look at this one, if we act on X, on these linear combinations on zeros and ones, we know that the computational basis is not an eigenbasis of X. So what you will see in essentially all these quantum computing operations is that we are going now to rewrite. So the first one and the third ones are straightforward to calculate and evaluate. But the one which causes problems is actually this one. So what we would have to do then is actually to replace x with a Hadamard gate times z times h times phi. Now you can now look at this as us acting on h multiplied with phi. So we could call this one for a phi prime. So that means that we could have an initial state. So we have an initial state phi, and then we act on this with a Hadamard gate, and then we get a new state phi prime. And we know that the Hadamard gate, when that acts on this linear combination, it has a very specific and very simple result. So if we have a state here, which is a linear combination, it will just keep this linear combination, but multiply it with a factor of 1 over square root of 2, with a plus or minus. So this is a pretty straightforward mathematical operation. But the thing now is that we can rewrite this term, which you see here. We can rewrite it as a d, and then I have this phi prime. Well, let's just write it like this. Multiply with z and phi, sorry, let me just, I was not meaning to do that. We have z and h times phi, which is the same as d times the state phi prime and z and phi prime. And this state phi prime is just a linear combination of the computational basis states 0 and 1. Okay? But what you see now is that if we want to set this up as a circuit, what you would have to do then would be something of the type like this. So you introduce the state phi, you act with a Hadamard gate, and then you have a Pauli Z gate, and this is actually our measurement at the end, and that gives us a phi prime here. But now I'm just setting this up as a circuit. Yeah. So you can, if you're now thinking of the way you do a measurement quantum mechanically, this is a measurement which acts on the computational basis states. So these are the states which you project out. If you take the Pauli X matrix, you could actually, from a computational point of view, and actually the code which I have at the end of the lecture today does that in a brute force way without thinking on how you would do that on a quantum computer. Because you can just set up this as a linear algebra operations and just run the calculations without thinking of a measurement. But the thing is that when we do this on a quantum computer, we are running measurements again and again. So an experimentalist would actually set these circuits up, and at the end, you would project out something. And then you simply count the number of times you have zeros and ones. And that parameter, which we have here, if you look at the, suppose you take the Pauli Z gate, and we go back to the state which we put up. And where did I put that one? Yeah, we have the state here. So this state, if you look at the measurement of that one with the Pauli Z gate, so the Pauli Z gate projects out one of them. What you would be doing then, in this specific case, is the following. So you would have a state here where you have an alpha complex conjugate, 0, plus a beta complex conjugate, 1. And then this has the Pauli Z operator here. And this is multiplied with alpha, 0, plus beta, 1. So when you do that theoretically, what you get now is simply what you would expect. You would have an alpha squared minus a beta squared. Now, experimentally, you would now simply run this many, many times as measurements. So a measurement means that the final state collapses to one of the computational basis states. So experimentally, if you now run n experiments, and we are going to mimic that when we run the theoretical calculations. So if you do run n experiments, you could now think that you measure n times 0, and you measure n1 times 1. So then your alpha squared is simply going to hopefully be given by n 0 divided by n. So n is equal to n0 plus n1. And finally, your beta squared is going to be approximately equal to n1 minus n. And then we can obviously invoke the law of large numbers, or Bernoulli's law. So Bernoulli actually spent 20 years of his life on actually proving what's called the law of large numbers. And it was based on a paper. So this was in 1720 something. It was actually based on an Italian mathematician from the 15th century who actually wrote this down in an intuitive way. His name was Cadarno. And Bernoulli actually proved that this is the case when you go to the large number of measurements. You should approach the result you would get from the distribution, if you know the distribution. There are distributions, however, which don't obey the law of large numbers. So you have distributions like, there are some Pareto distributions or Cauchy distributions as well, which actually don't behave like that. But if you take a Gaussian, that would be a typical example, which obeys the law of large numbers. So this is a typical thing which you will run. So you're gonna, and in the literature, you probably saw and also in the example from last week, we called an experiment for one shot. So you run 1,000 shots. To me, shots is a strange word because I tend to link that with something else. But so I'm going to say measurements. Yeah. Shots makes me think of Fridays and Saturdays. Okay. Anyway, so this is essentially what we end up doing. And one of the reasons why we don't do, as you said, just perform the calculations, is simply because we want to make a measurement at the end. So these are the kind of, how to say, overarching motivation for what is coming now, and why I also wanted to bring back some of these games. What we are going to do next now is to look at these rotation matrices, because there are some technicalities which we need to carry with us. So the thing which we would need to bring back again now is this notion of a block sphere. And it's not a good practice to introduce a new topic before a break. And I see now it's 3 o'clock, so let's take a break. And then we start with the block sphere after the break. And then we are going to look at these rotation matrices and how we can use these to make an ansatz for this trial wave function, which we put up here. Because that, for the 1 qubit state, is going to represent a random position on the sphere. So it would be any state. And we don't know if that state is the one which gives us the energy minimum. So we will just choose random angles and then simply optimize or perform an optimization, set up an optimization algorithm, which then finds the angles which gives us the lowest energy. So we are targeting the variational principle, targets the lowest lying state with a given symmetry of a specific Hamiltonian. Any questions so far? We'll take a small break. Is that okay with everybody? Okay, so let me just do that. Okay, so the thing which I wanted to just briefly illustrate, because I know that many of you have seen these things before, is then to just make an attempt at drawing a sphere. So I am according to my wife, and my daughter always agrees with my wife, I'm a one-dimensional guy. So venturing into 2 dimensions is already very difficult. Making a 3-dimensional drawing, yeah, it's going to be if I make it, I'm going to take a selfie with it. Sorry, guys. But what you could think of is that we have let's just put up the axis. So you could now think of the state 0, which just points north. So you could think of the state 0 as a projection. So I'm just going to write it like this. So this is the state 0. And then when you think of acting with the Z matrix, you know that you get -1 times the computational basis state 1, qubit 1. So when you look at the action of the Z matrix, you could now think of the computational basis state 0 to be a projection along the Z-axis pointing upwards. You could think of that as the north pole. And then you could have the other state, which would be our 1 state, as the one which points downward to the south pole. So this is a typical way of illustrating the computational basis which we have. So the Pauli Z matrix projects out along the Z-axis. Now we know that a point on this sphere could be represented by this vector. We would have an angle theta, and then we have the projection, and then we have an angle phi here. So I'm not going to draw a sphere, but what I'm going to disappoint you guys. This is way too much for me, actually. But what you could say now is that every qubit system, so we are thinking of a single qubit now, that can be visualized as a point on this block sphere, or on this sphere, on a 3-dimensional dim sphere. And then we have a radius, which is equal to 1, with a radius 1. We have this r equal to 1. And angles theta and phi. So what we could think of then is that we have an arbitrary state with some arbitrary angles, which will simply then be written by some cosine. I could write a theta or theta half. This is just conventions. Theta half plus an e, there's a phase factor of phi, multiplied with sine. And this is, sorry, I have to be a little bit careful here because so I don't forget things. So this is multiplied with 0 plus. So I'm not proving this relation here, I'm just stating it. Multiplied with 1. So this would be a general state. And you can obtain this by performing operations with rotation matrices. So this is where the rotation matrix comes in. And if you look at a rotational around an angle theta, this for a 2x2 matrix, this is represented by cosines and sines. So the rotation matrices, and these are specific convention. So we have a rotation along the x-axis. An angle theta is given by E of theta half multiplied with a Pauli X matrix. A hat? Yeah. So this is just a convention which is used in the literature. So I think there is a deeper geometrical meaning, but I don't remember properly. Yeah. Yeah. Exactly. Yeah. Yeah. There's a deeper geometrical meaning there. Yeah. So I've forgotten that one. Sorry. You get so used to just use the expressions. So this is something when you now perform a Taylor expansion of the exponential, you can rewrite that as cosines and sines, as you probably have seen before. So that means that this can be rewritten as a cosine of theta half multiplied with the identity matrix minus an I times sine of theta half. And this is then multiplied with the X matrix. And then you can do the same thing with a rotation along the y-axis and similar rotation around the z-axis. So I'm just setting up the definitions here. So you would have an ry of theta, which is then again a cosine of theta half multiplied with the identity matrix minus an I of sine of theta half multiplied with the y matrix. And the rotation around the z-axis is then, we can actually rewrite this since these are 2 by 2 matrices. We can also choose to write this as a matrix. So if you do that, this would simply be given by e to the minus I theta half 0, 0 of e to the I of theta half. So that's the rotation around the z-axis. And there are some operations here which you can look at as an exercise. So just as a small exercise, you can show that if I act with X times the RC matrix, or the rotation matrix, this is the same as RC minus theta. We are going to use some of these operations and identities when we are setting up the derivative of the trial wave function and the energy. Now, I'm just anticipating something which is coming, because we are going to take the derivative of the energy expectation value as a function of these variables, theta and phi. So these are the variational parameters. So think of now us preparing an initial state in terms of an Rx and Ry rotation. So what we could think of now is an initial state with random angles, phi, which is given by an ansatz where we now could take, suppose we could have a operation along the y-axis, and then we have a new angle around the x-axis, and this could be multiplied with, so this is a ansatz, so we could start with a qubit 0 as an initial state, and then we rotate it so that we actually end up in a random position on the Bloch sphere. And these angles, theta and phi, are then treated as parameters. So that means that what we have here is a function which depends on theta and phi. And when it comes to the variational principle, we are going to use these as parameters. So that means that this is our ansatz for the trial wave function. And we are going to use that ansatz to calculate the expectation value of the energy. So that means that what we will calculate now is the following quantity. We are going to calculate, I don't think everybody has finished to write. So when we have this ansatz, what we are going to calculate is actually this expectation value. So we have a function of these angles, which could be just random angles on the Bloch sphere. And this is then multiplied, so we take the expectation value of these quantities here. Now, the energy is in general represented by a convex function in these variables. So what we are going to do then is to implement a minimization algorithm. That means that we are going to need derivatives of this quantity with respect to the angles. So we will need, if we want to apply the variational quantum eigensolver, we will need for the VQE. So VQE stands for the variational quantum eigensolver. We will need, so let's call this the energy. So I'm not writing the expectation value, I'm just writing this as the energy as a function of theta and phi. I have two parameters. So we will need for the VQE to optimize this E theta of phi. And the standard way we do that is to calculate the gradients. We have two variables, and we want to drive them to zero. So what we want then is simply to calculate this quantity here, d phi equal to 0, and we want a d of E of d of phi equal to 0. So this is going to be the optimization part. So next week, we are going to actually discuss how we can implement this optimization part. But today we are going to do this in what I would call the brute force way. We are simply going to make an ansatz in terms of these rotations. And then we are going to calculate the energy just in one shot and see what we get. Now, this will most likely not be the optimal wave function. But the whole idea behind the variational principle is that we have, and let me now just remind you of the variational principle. So what we have is, so probably most of you have seen that in some basic courses in quantum mechanics. So what we have is we have a Hamiltonian here, which when it acts on the exact wave function is now given by E times psi. So psi is now the exact wave function. So this is we have an eigenpair. We also know that this Hamiltonian may have a spectrum of values. So what we could have then is that we have H acting on a set of these functions, and that gives a set of eigenvalues, psi of n. So this is an orthonormal basis. So we would have a psi of n multiplied with a psi of m is given by the Kronecker delta here, like this. This means that I can actually expand any state in this basis. So it means that this ansatz which I used, and now I'm going to take away the angles. So the ansatz phi is something which I could now expand in terms of this basis. So I could have now a sum. In principle, this is an infinite basis. I have some overlap coefficients between that specific state, the ansatz, and the basis which I have chosen, like this. So then what I can do now is to insert this expression for the ansatz which I have in the expectation value of the energy. But I have to be careful because I also need to take into a normalization constant. So when I then calculate my expectation value of this specific state, I need also to bake in a normalization constant. This is a discrete sum here. So I would have n and m, and then I would get the, not that one. I would get a C of n complex conjugate, a C of m, and then I have my basis, psi of n, with psi of m here, divided by a normalization constant, which is now running like this. And then I have assume now that I use the orthogonality of the states. And then we know that in case this phi is given by one of the states, then I have the exact energy. But in general, and if I order these states, so I can replace this one then in terms of the eigenvalues. So I end up with a sum, which is now given by the eigenvalues, just a constant here, divided by the normalization constant. Now, these normalization constants, if I sum them up, because I require that that state is normalized to 1, so you could replace this sum over these normalization constants to 1. And then we know that if we organize the states like this, E1, E2, etc., up to some final, in principle, we have an infinity of states. So if I obviously have the exact wave function, and if that corresponds to psi 0, then all the other terms disappear. And then I'm simply left with a C0 squared times E0, and then C0 is equal to 1, C0 squared. And then, but in general, then what I see is that this energy here, which I'm calculating, is going to be larger or equal than the lowest energy. It's going to be equal in case we have the exact solution. If not, it's going to be larger than the exact one. So this is just the variational principle, the way we are using it now in a nutshell. Okay? So what we need is now to set up, and essentially what the variational quantum eigensolver is doing is now to start with an ansatz. And this ansatz is going to be given by the state which you see here, this one, for the 1 qubit state. So we just pick a random state on the Bloch sphere. With that random state, we can obviously now perform the rotations, and we can simply calculate this expectation value. And then if we go back to this Hamiltonian which we have, we can then compare with the exact eigenvalue. Okay? So let's go back to the Jupyter notebook, because then you can see the basic steps which I'm going to implement in order to set up the variational quantum eigensolver. So the whole idea is actually pretty simple, and it's a mix of quantum operations and classical operations. And the classical part is the one where we perform the optimization. And that optimization leads to what many of you have encountered as gradient methods. So who has never dealt with a optimization problem? So think of convex optimization. You have a convex function, right? And the typical way you implement that numerically is by calculating the gradients. And then when you have the gradients, because what we want to drive to 0 is not the expectation value of the energy, but we want to drive to 0 the gradients. So the standard method is the famous Newton-Raphson method. That's what everybody implements. And that is essentially based on us making a Taylor expansion of the expectation value of the energy around the optimal values. Then we truncate the Taylor expansion at the level of the second derivative. And then we hope for the best, that we can neglect those high order terms. If you do that, then you can derive Newton-Raphson's method, which at the end, what it means is that we are going to have an update rule. Yeah. Yeah.
But that occurs if you're near local minimum, or what happens if you have like several local minima?
That is a very good point. So in this kind of optimization theories, what many people often end up using then is stochastic gradient descent, which is a way to hopefully place you in such a position that you can explore more minima. But this is actually a big research field on how you find the global minimum. Now, there's one thing with Hamiltonian type of problems. I have never encountered a Hamiltonian type of problem which does not have a global minima and which normally only has a global minima for specific symmetry. The type of problems I've been dealing with have essentially just had a function which is nice and convex with one well-defined minima. But you can encounter problems. You have no guarantee that you can be stuck in a local minima. You don't have that. And for those of you who have taken a course in machine learning, you know very well that optimizing a multidimensional function is highly non-trivial. And this is actually in machine learning, if you think of, let's say, setting up a neural network, which in the mathematics of a neural network is nothing but high school derivatives. It's just chain rule applied, plus matrix multiplications. But the tricky part is the optimization part. And then you need to optimize a multidimensional object. And that is a big topic. And that's where a lot of research in machine learning actually is going on finding better ways of finding this minima. So if you think of a plane gradient descent, and this is something which we will look at in more detail next week. So if you look at these parameters, if we now just set up a common denominator, so the standard way of doing this is to actually do a gradient descent and variance of gradient descents. And you will see if you go into that review article by Tilly et al., you will see a description of different ways of finding this minima. But the standard gradient descent, if we now use a general parameter, W, which now contains theta and phi, so this is now a container for the parameters. So what we would do then is typically to have an update rule, and this is Newton's method. So we would have W, which is being updated. So we have the previous value minus, and then we have the gradient of the energy as a function of these parameters. So I'm just writing this as a gradient W of the energy, which is a function of theta and phi. Now, since you want the roots of the gradient, it means that in front here, there should be the inverse of the second derivative. So if you think back of Newton's method, so in Newton's method, what you have is f of x. You want that to be 0. And Newton's method gives you an update rule, which goes like x of I plus 1. The next iteration is given by x of I minus f calculated at x of I divided by f of x of I. That's Newton's method for just a one-dimensional problem. So the way I've wrote it here is just a more compact way of showing this iterative process. We start with a previous value. You calculate the derivatives, the gradient. But here, what happens now is that in principle, in front of this expression, we should now have the second derivative. If I have many variables, this is the Jacobian matrix. And in the literature, this is called the Hessian matrix. This is often a complicated quantity to evaluate. And that means that in the literature, you actually include just a parameter, which is often called the learning rate. This can be something which depends on an iteration. You would typically tune this parameter to find the optimal minimum. So typically in the calculations, if you don't want to calculate the second derivative, which is often much more involved, and if you have many parameters, you have to calculate the Jacobian matrix, and you have to invert it, and that can be time-consuming for every iteration. So if you have 1,000 parameters, then your Jacobian matrix is 1,000 times 1,000, and if you're doing 100 iterations for each parameter, so 100 times 1,000, that's the number of operations you're doing. And in every one, you're going to invert a matrix, which is 1,000 by 1,000. And you don't want to do that. So all these gradient optimization methods, they are often focused on you finding ways to calculate this one with as much knowledge about the second derivative as possible. So I always say, half jokingly, that if you can cook up a very efficient method and reliable one, you will get many, many new friends. And these are friends which will cite you. So I'm not inferring that you guys don't have friends, but these will be friends because there's a method. And for those of you who have taken a course in machine learning, this is really a hot research topic. There's a method which is called ADAM, Adaptive Gradient with Momentum, which was presented in 2014, and it has 150,000 plus citations. A good physics paper, a good mathematics, a good science paper has 100 plus citations. So that tells you the order of magnitude of interest in this field, in the optimization. So we are going to implement something like that next week. And we are going to use a library from Scientific Python, which employs quasi-Newton methods. And there's a famous one after a guy called Broyden, which is a modification of the second rule, which actually sets up a kind of guess for the second derivative. And that's a very popular method, which avoids calculating the second derivative. If you can calculate the second derivative here, then you should obviously use it. But keep in mind that this this is actually Newton-Raphson's method, what you see here. That is based on a Taylor expansion of the energy, the expectation value, truncated at this level of the second derivative. That is what allows you to derive Newton-Raphson's method, which is one of the famous methods for finding the roots of a function. Any questions so far? So this is a technicality, but this is the classical part which we need to implement. Then we obviously have the quantum mechanical part, or the quantum computing part, which means that we have to set up the operations as gates. In real life, when you run this on a real quantum computer, gates are actually manipulations of states with lasers or magnetic fields, or one or the other way by which you can manipulate the states. For us, these are, in this course, they are just going to be mathematical operations. So let's continue a little bit with the Jupyter notebook and take a look at the VQE method. So this was from last week, so we should actually go back to this one. So what I wanted, so the basic steps of the VQE is to prepare the variational state with some given angles on a quantum computer. Then you measure the circuit in various bases and send these measurements to a classical computer, which performs the optimization. And then the classical computer post-processes the measurement data to compute this expectation value. And then this classical computer varies the parameter theta according to a classical minimization algorithm and sends them back to the quantum computer, which then runs step one again. And then we repeat it till the gradients are as close to zero as we want, or as close to zero as what you define as zero. So that's the essence of the variational quantum eigensolver. So for those of you who are familiar to variational methods like variational Monte Carlo methods, I know that some of you are studying that this semester. This is essentially just a variant of that. Except that now we are performing all the operations on the states with various quantum gates. So if we now go back, so I'm just going to scroll down. These are things which I will repeat a little bit, but we are going to look at the first part of the project, which is the part beyond the Bell states. And that means that we are back to this simple Hamiltonian, which we discussed. And this is the same Hamiltonian which we have in the project. So this is our warm-up case of the implementation of a quantum eigensolver. And as we saw, we can rewrite this. We assume that these are eigenstates of the one part of the Hamiltonian. So this is a computational basis. It means that the eigenvalue of H is a linear combination of 0 and 1. So when you diagonalize, you get the coefficients, which are the linear combinations. Is that okay? So that's the diagonalization part. So we have a computational basis. This basis is not an eigenbasis or the full Hamiltonian. The eigenbasis or the eigensolution or the full problem is a linear combination of these two. And when you diagonalize, the eigenvectors you get are the coefficients in terms of 0 and 1. So as we discussed up and down in the beginning of the semester, we can rewrite this in terms of poly X, poly Z, and matrices and the identity matrix. So this is essentially the first exercise. So I'm not going to plot this again, but if you now run it and we look at the eigenvalues, we should actually get this as an eigenvalue. With the parameters which I chose here, I put epsilon 0 to 0, epsilon 1 to 4, the non-diagonal term to 0.2, this one by 3, and then I simply diagonalize. So this is what we should get, okay? Now, what I could do now, I can obviously rewrite everything. I'm preparing for the quantum calculations. I can rewrite everything in terms of poly matrices. I have the identity matrix. So now I'm just writing the Hamiltonian in terms of the different matrices. So I should obviously get the same, right? And fortunately, I got the same. So I haven't done something wrong. So I'm just preparing. So this is something, I'm saying this because when you're writing the project and writing the code for it, it's useful to actually do this kind of baby steps. It's easy to make small errors in coding the poly matrices. Just ask me. I actually did that. If you look at this one, 0, 1, I had them interchanged. And I spent some hours in finding out why I didn't get the same result. So it's useful to actually do these kind of exercises. So what I'm going to do now is simply to take the 1 qubit system, and I'm going to make, so on the whiteboard, you saw the drawing of the circuit now. So we have an Rx gate and an Ry gate. And phi and theta are angles which we can choose randomly as starting values. So what we know is that this is here, due to the mathematical form of the matrices, is going to give us a linear combination of the computational state 0 and the computational state 1 when I act on these. And I have 2 parameters I can play around with. Then what I'm going to do now, and this is one of you asked before the break, why don't we just compute this with this? And this is what this code is actually doing in the beginning. So I'm just setting up my Hamiltonian in terms of these poly X and poly Z matrices. And I have these ansatz here. And these are the rotation operators which we are setting up. They look like this for Y and X. And these thetas and phis are just angles. So what I do now is just, instead of picking randomly theta and phi, I just fix them to a specific value. And then you see now that I have Rx and Ry. I define my basis. This is my computational basis, and this is what we want you also to set up. You can run everything with Qiskit, but we want you to set up the computational basis. This is just the simplest possible way of doing that. And keep in mind that the codes which I present here, there's nothing fancy, no object orientation, no nothing. If you go into Hunt's book, that is as a set of codes which do the same things, but are written in a more professional way. So I'm just setting this up in the simplest possible way so it is pretty transparent. And then you see immediately the connection with the mathematics, okay? And what I'm doing now, I'm setting up the rotation in X, rotation in Y. And you see immediately the straightforward implementation. My new basis, so this is a state, which I'm going to use to calculate the expectation value of the energy of. So I'm just simply plugging, this is my new basis, and you see then that the energy is just a new basis. And then here is another thing which I actually forgot, because when you're writing codes, you want to get the answers as quickly as possible. And I had forgotten to take the conjugate transpose. So you have the new state is actually this one, but when you calculate the expectation value, you have to take the conjugate transpose here, okay? And I forgot that one, and that gave me an imaginary part which was different from 0. So that's a pretty good test, because your eigenvalues should be real. So if you don't get real eigenvalues, you have done something wrong. And that was another 2-3 hours which I wasted, because you forget things, right? Yeah, so that is 0. But in the beginning, if I didn't do that, if you now take this one, if you take this one, if you forget to do that, which I did, and I couldn't understand why so let's now just do that, and I rerun it. Then you have an imaginary part which is non-zero. So that's a useful test that things are running correctly. Now, this is not the way we are going to implement it. So the way we are going to implement it now is one, as you can see here, what I'm doing now is being inspired by this. I didn't get a very good result, as you can see. So let me just bring that one back and just rerun it. So what you see, you have 2, but we want 0.98. So what I'm going to do now is to do something which is not very smart, but I'm simply going to run over a set of angles. And now I pick these angles I just arrange them from 0 to 180, take 10 values. And then I initialize it, and I calculate the expectation values as a function of these angles. So there's no minimization here. I'm just in a brute force way producing an array of results. And then I pick the minimum difference, which is here, or the expectation values. And now I have a difference which is 0.015. So that's getting a little bit better. But this is not a very intelligent way of doing it, because I'm simply computing this without computing the gradients, without using an optimization scheme. I'm simply calculating in a brute force the eigenvalues or the expectation value of the energy with different angles theta. Nothing but that. So there is no optimization here. Now, the reason why I want to state this is simply because, as I say here, this is not the very best way of proceeding. We are not performing measurements either. We're just calculating. So the kind of quantum computing which we want to include by performing a measurement on the states is not included here. This is something which would just be another variant of an optimization problem, or you calculating the energy for a set of trial wave functions. And then with that array, you're searching for the minimum. There are several reasons here for why this is, I just want to demonstrate how you would start setting up things, because the rotation matrices, we can use their properties to find analytical expressions for the derivatives. So this is going to be important in the real implementation, because if you go back a little bit to the whiteboard, and this is an important point which we will discuss in more detail next week. If you look, no, sorry, I didn't click on the right one. If you look at the expression which we have for Newton's method, when we are trying to find the optimal parameters, you see now that I'm calculating a gradient here. Now you can calculate a gradient in a brute force way, by just using finite difference methods. But the thing which is nice with these rotation matrices is that we can obtain analytical expressions for the derivatives in terms of the rotation matrix as a function of the angles. And that's extremely useful, because then we have an efficient rule to set up this quantity, which is normally time-consuming numerically if you're using a finite difference scheme, or if you're using automatic differentiation. So we will derive these equations next week. With that, we can implement the optimization, because we have the expectation value of the energy, we have the expression for the gradients, and we are going to perform measurements at the end. And we are going to rerun these calculations again and again, and we will take the averages after many, many runs. So this is a plan for next week. So I just wanted to use this kind of less intelligent way to prepare the ground for what we are going to implement next week and what kind of elements we are going to need here. So here we will also see the Pauli Z matrix, which we are rewriting in terms of Pauli X, in terms of the Pauli Z and Hadamard. And this is something which allows us to rewrite the Hamiltonian so that we are going to calculate this expectation value, this one, plus that one. So the plans for next week is to start from there. We are going to discuss how to perform experiments for simpler 1 and 2 qubit Hamiltonians, which we have in the project. And then we are going to try to simulate efficiently Hamiltonians on quantum computers with a VQE method, and using gradient descent to optimize the state function ansatz. So that at the end of next week, we are going to have a more, how to say, a code which is closer to the way you would implement the VQE. And then we are going to look at a more interesting Hamiltonian than this simple 2x2 and 4x4 matrices. And there is a famous one in theoretical physics, which is called the Lipkin model. And some of you have met it and have had nightmares about it, probably. But you can actually rewrite this in terms of Pauli matrices. And that's why this is so popular. And there are other Hamiltonians, model Hamiltonians, which are written in terms of Pauli matrices, like you have the Heisenberg Hamiltonian and other spin-like Hamiltonians, which have been very popular in studies of quantum mechanical systems and quantum computers. So I hope you see the wood for the trees and what kind of ingredients we will bring in next week. And when we have these ingredients, we can then add more complicated Hamiltonians and try to simulate those. And that's essentially the ingredients which you need for the finalization of the first project. Any questions? Things which are unclear? Okay, I hope I'm not going too slowly ahead. Hope the pace is okay. Just let me know if that's okay. Okay, I'm going to stop the recording.